The universe, in all its vastness and complexity, has fascinated humankind for centuries. Among the most profound questions that scientists and philosophers have pondered is the origin of the cosmos. The prevailing scientific explanation for the beginning of the universe is known as the Big Bang Theory. This theory suggests that the universe originated from an extremely hot, dense state and has been expanding ever since. The science behind the Big Bang is based on a combination of astronomical observations, theoretical physics, and mathematical models. We will explore the origins of the theory, the scientific evidence supporting it, and the implications it holds for our understanding of the universe. The idea that the universe had a beginning is a relatively modern concept in scientific history. In the early 20th century, physicists and astronomers began to challenge the long-held belief that the universe was eternal and unchanging. One of the first indications that the universe might have a beginning came from Albert Einstein's general theory of relativity, 1915. This theory described gravity as a curvature of spacetime and hinted that the universe could be dynamic, rather than static. However, it was Georges Lemaitre, a Belgian priest and physicist, who first proposed the idea that the universe originated from a single point, which he called the primeval atom, or the cosmic egg. This idea was later refined by other scientists, including Edwin Hubble, whose observations of distant galaxies provided critical evidence for an expanding universe. In 1929, Edwin Hubble made a groundbreaking discovery that fundamentally changed our understanding of the cosmos. Using the Mount Wilson Observatory, he observed that distant galaxies were moving away from us. More importantly, he found that the farther a galaxy was, the faster it appeared to be receding. This relationship, known as Hubble's law, provided strong evidence that the universe was expanding. If the universe is expanding now, it implies that in the past, it must have been much smaller and denser. Extrapolating back in time suggests that the universe started from an extremely compact state. One of the most compelling pieces of evidence for the Big Bang Theory was discovered in 1965 by Arno Penzias and Robert Wilson. While working with a radio antenna at Bell Labs, they detected a faint but persistent background radiation coming from all directions in space. This radiation, known as the cosmic microwave background, CMB, is the afterglow of the Big Bang, a remnant of the hot and dense state of the early universe. The CMB is incredibly uniform, which suggests that the universe was once in thermal equilibrium before expanding and cooling over billions of years. The Big Bang Theory also explains the relative abundances of the lightest elements in the universe: hydrogen, helium, and lithium. According to Big Bang nucleosynthesis, BBN, the early universe was hot enough for nuclear fusion to take place, leading to the formation of these elements. The observed abundances of these elements match the predictions made by the Big Bang model, further strengthening the theory. The distribution of galaxies and cosmic structures in the universe also supports the Big Bang Theory. Over time, small fluctuations in the early universe's density grew into the vast cosmic web of galaxies we observe today. These structures formed due to the influence of dark matter and gravity, which shaped the evolution of the cosmos. While the Big Bang Theory explains much about the origins of the universe, it does not fully address some key questions, such as why the universe appears so uniform on large scales. To address this, scientists developed the inflation theory. Inflation, first proposed by Alan Guth in 1981, suggests that the universe underwent an extremely rapid expansion in the first fraction of a second after the Big Bang. This period of inflation would have smoothed out irregularities and set the stage for the large-scale structure of the universe we see today. Understanding the origins of the universe naturally leads to questions about its ultimate fate. The expansion of the universe continues today, driven by a mysterious force called dark energy. Depending on the nature of dark energy and the overall density of the universe, there are several possible scenarios for its future. The Big Freeze, heat death. If the expansion continues indefinitely, galaxies will drift apart, stars will burn out, and the universe will become cold and lifeless. The Big Crunch. If gravity eventually overcomes the expansion, the universe could collapse back into a hot, dense state. The Big Rip. If dark energy continues to accelerate the expansion, the fabric of space-time itself could be torn apart. Current observations suggest that the universe is on a path toward a Big Freeze, but further discoveries in cosmology may refine our understanding. The Big Bang Theory stands as one of the most significant scientific achievements in our quest to understand the cosmos. Based on a combination of theoretical physics and observational evidence, it provides a compelling explanation for the origin, evolution, and structure of the universe. From Hubble's discovery of an expanding universe to the detection of the cosmic microwave background, each piece of evidence reinforces the idea that the universe began as a singularity and has been evolving ever since. While many questions remain, such as the nature of dark matter and dark energy, the Big Bang Theory continues to be the foundation of modern cosmology. As technology advances and our ability to explore the universe improves, future discoveries may provide even deeper insights into the origins of everything we see today.